Okay, let's continue with node voltage analysis, and this time we will look at an example problem. Okay, so the theory is covered, the steps and the methods are covered. Now we'll solve a circuit. And I particularly like this example. Let's see, let's bring up. Okay. So the circuit has 4 resistors and 2 current sources. Okay, 2 current sources. All of the resistor values are given, right? 4 resistors, all values are given. Now, when you are, when you're working as an engineer, when you're working as an engineering student, you're presented with a system. That system would have illustrations, would have some figures, and have some words. In this case, we have what is known as a circuit diagram. So circuit diagram is given to us, notations are given to us, and then the values, the components are given to us. And the question asks is solve for all branch currents and node voltages. That should be node voltages. Okay. Node voltages. So when you first look at a system like this, you extract as much information as you can about that system and about the problem. Sometimes the information is embedded in the image. Okay, in this case, it's not, but as you saw in quiz 1, there's information and there's some homework problems. The information is embedded in the circuit diagram itself. So always extract as much information as you can from the given circuit diagram and then proceed. So what is the first thing that you need to do? If you're asked to solve using node voltage analysis, first thing is to identify all the nodes present in the circuit. So how many nodes do we see? 1, 2, 3, 4, 5, 6. I have 6 nodes. How many do you have? Anyone online would like to state an answer? There's no penalty for guessing. Okay, let's put it this way. How many of you agree or disagree with, how many of you agree with 6 nodes? One person agrees. Only one, that's it. 2 people agree, 6 nodes. Okay. And Jordan, you stated 10. Okay, so you counted 10 nodes. Anyone with 10 nodes? Okay, another student, so 2 students with 10 nodes. How about the rest of you? Any guesses? No other guesses? Wild guess? All right, again. So it's not quite a trick question. I'm using it as a teaching moment. If you have 2 nodes in a circuit, we go back to the definition. Node is a junction point in a circuit. Any wire, whether it's a dot or a dash, is a node, right? So if you have 2 nodes in a circuit, especially this kind of circuit diagram where you have a dot marking a connection like this one, it's going from one component to another component, making a connection. If you see 2 of these dots in a circuit, meaning it's connected with a wire, and there is no other component between those 2 nodes, what do we think it means? If you take a 100-foot extension cable, plug it into a power outlet, do we expect 110 volts at the other end? Yes, it's the exact same node. So if you have 2 nodes connected with a wire, then it's the exact same node. And so this is one of the hardest things is one of the hardest things to actually do when you first begin circuit analysis, which is identifying all the nodes. And that's why I'm emphasizing this, you know, especially. So I want to emphasize this. This is a learning moment. Okay, so it's not about making students feel bad. This is I want to use this as a teaching moment. If you have two nodes in a circuit and there is nothing connected between those nodes except for a wire, then electrically speaking, it's the exact same node. And so if you look at this, there's a wire here. So this is the exact same node. And so is this. And so is this. So electrically speaking, doesn't matter how the circuit diagram is drawn. This is node A. This is node B. And this can be C. So there's only 3 nodes in the circuit. Let's take a 10-second pause while you think on those fundamentals, and then let me know if you have any questions. Okay, A, B, and C. Node A, node B, and node C. What else do we see? If you have multiple components connected to the exact same 2 nodes, are those connections in series? Are those components in parallel? What can we say? You have 2 or more components connected to the exact same 2 nodes. What can we say about those components? They are in parallel. R3 is connected to A, and so is R2. And they're also both connected at B. So even though it doesn't look like it, just from this diagram itself, but R3 and R2 are in parallel. And it's tricky and it's a little bit hard to see directly from the visual image. Okay. But they are in parallel. So we can first begin by reducing R3 and R2 in parallel. So R2 in parallel with R3. I'm going to call that as, let's see. Label it as R23. In R23 would be equal to R2 is 2000 and R3 is 10,000. Therefore, R23 is 1,666.67 or 0.667 ohms. Okay. So that's what now you can solve the circuit even without reducing R2 and R3. It will just take, a couple more steps. So reducing R2 and R3 simply makes the solving more efficient. Okay, so we identified the 3 nodes, and I'm going to redraw the circuit now. With R23. When you're drawing these circuits for the quiz or for the exam, make sure they are large. So when you place notations on there, that's easily legible. Oh, that's a current source, not a voltage source. Okay. So I1 is going up, I2 is coming down, 2, 3, R1, R2. Sorry, R1 and R4. And node C will be a reference. Therefore, VC is equal to 0 volts. That's node A, that's node B. That's the initial setup. Okay. I identified all the nodes and I chose my reference node as C. So VC is automatically assigned 0 volts. So how many unknown nodes? 2 unknown nodes. So we need at least 2 equations to solve for these. Okay, so the next step now is to assume the branch current directions. Now again, reference node can be A, can be B, can be C. We chose C. Again, as you are solving it yourselves, you can choose any node and you'll still obtain the exact same answers. It won't be any different. Okay. Now the node voltages would be different, again, because your reference point is different, but the actual voltage across the resistors would turn out to be the same. That will never change. So I'm going to make some assumptions based on the direction of the current sources. Okay. And the assumption I want to make, of course, is that I1 is going up. Right? I1 is going up. Then it splits into 2, goes down R1, and it goes through R23. So I'm going to label this as IR23. And this is R1. So I'm going to call this IR1. IR4, also I'm going to choose coming down. And that's it. I only have 3 resistors, 3 branch currents. IR23 goes from left to right, and IR1 and IR4 are coming from the top. You all with me so far? Let's take a pause while you write it down. Let me know if you have any questions. Any questions? Okay. All right, so then I'm going to write down the voltages. VR23 would have a plus on the left, minus on the right. VR1 would be plus at the top, minus at the bottom. And VR4 would also be plus at the top, minus at the bottom. And that is because of the assumption of the current direction. Okay, that is the setup of the problem. Yeah. Okay, and these are the most important steps. If the setup of the problem is incorrect, then the rest of the solution would be incorrect. So now apply KCL at A, and you write out your equation. I have I1 entering and IR1 and IR23 leaving. I1 is IR1 plus IR23. Then apply Ohm's law. Ohm's law gives me VR1 over R1 and VR23 over R23. Okay. First step was to write the KCL expression. I1 is IR1 plus IR23. And the next step is, of course, applying Ohm's law. I1 equals VR1 over R1 and VR23 over R3. Now for the next step, we'll just combine those two together, and I'm going to express each resistor voltage in terms of the node voltages, and then I'll also plug in all the known values at the same time. Okay, so what are my known values? My known values are R1, R23, and the current source I1. And then if I express each resistor voltage in terms of the node voltages, I have VR1 connected between A and C, and the current comes from the top. VR1 has a plus up top, minus at the bottom, and so VR1 can be expressed as VA minus VC divided by R1, which is 1000, and VR23 is VA minus VB divided by 1666.667. And then I1 is 10 milliamps, is 0.01. Okay, you plug in all the known values and you obtain your coefficients. Now, after this step, I'm going to multiply the entire equation by 1000. I'm going to remove the denominators, and so I will obtain minus 0. Oh. This is VA minus VB. Reduce this expression and you obtain VA minus 0.5999. VB is equal to 10. And I'm going to call this as equation 1. Let's take a pause. Let me know if you have any questions. Any questions so far? Do the steps make sense? Good. Okay, then let's write our second equation at node B. And this time I'll move a little bit faster. Okay, so I'll go here on the left. KCL at node B. And at node B, I have IR23 coming in. I have I2 leaving, and I have I4 also leaving. So I'm going to write IR23 equals IR4 plus I2. Apply Ohm's law. I can write VR23 divided by R23 equals VR4 over R4 plus I2. VR23 is VA minus VB divided by which is equal to VB minus VC divided by 2000 plus 0.05. That is my equation. You solve this, I'm going to say multiply this with 2000 Then I have my second equation, 1.199 VA minus 2.1999 VB equals 100. And this I'm going to label as equation number 2. Solve the two equations with any method you choose. Program it into your calculators, solve them manually, use MATLAB, doesn't really matter how you want to solve it. Once you solve these, the answers VBA is minus 13.569 volts and VB is minus 52.857 volts. Let's take a pause, a longer pause this time, while you write everything down, and let me know if you have any questions. And then I will do a recap just afterwards. No idea. I think that maybe they're upgrading the chairs in the classrooms, perhaps. All right, any questions? Do the steps make sense? Does the methodology make sense? What do you notice about the final answers? Negative values. But does that mean our answers are incorrect? No. The only thing it means is that relative to our reference node, both values, both nodes A and B are below our reference node. So if I was to plot, if you want to plot that single dimension figure for those 3 points, C is my reference node. So C is somewhere here. Okay, this is node C. That's 0 volts. A is minus 13 with reference to C, means it is below C. It's below sea level. And so A is here. Of course, this is not to scale. 569 volts. And then B is somewhere here. Minus 52.857 volts with reference to C. That's all it means. Doesn't mean anything else. Remember the example I said, measuring the height. If I measure my height with reference to the floor of the room or the seat of the chair or the surface of the table, the height always remains the same. So in this case, if C is my reference node, then C has a value of 0 volts for the purposes of this calculations only. C is 0, A is minus 13.56, and B is minus 52. Then I would like to point out if A is a reference, then V is 0 volts. So in that case, my diagram still remains the same. A is here, B is here, and C still remains here. A is now 0 volts, and C would be plus 13.569 volts. And B would be, what would be B? About 39 minus 39 point some volts. 13.56. 0.857 minus 13.569. 39.288. Think over that. Let me know if it doesn't make sense. Let me know if you have any questions. Okay. The important point being, it doesn't matter which is your reference node. What you choose as a reference node has no bearing on your final answers. Your node voltages would be different, right? Because your reference point is different. But when you plug in these node voltages into your equations, you would obtain the exact same resistor values. If A is your reference, VC is plus 13, VB is minus 39. If B is your reference, VB is 0, VA, the node voltage, would be plus 39, and VC would be plus 52 volts. Does that make sense to everyone? It's a very important point. And you take these answers, you take these node voltages, and you can plug them into any equation. If you wish to find the resistor voltage across R1, VR1 is VA minus VC. You simply plug in the values for VA and VC in there, you get the resistor voltage for VR1. If you wish to find IR1, it's VR1 divided by R1. So simply plug in the values. Too small. Does that make sense to everyone on how we determine resistor voltages and currents from node voltages? Once you have your node voltages, you use the equations you generated at the beginning of your analysis. You plug in all of the node voltages wherever you wish, and you determine all of the unknown voltages and none of the currents. And that is the key point. Your node voltages might have different values depending on your reference nodes, but the resistor voltages and the resistor currents will remain exactly the same as any other student. Okay. So 3 students could choose 3 different reference nodes, would have 3 different answers for node voltages, but the resistor voltages and the resistor currents that they determine would be exactly the same. So again, going back to the important point, it doesn't matter what you choose as your reference node, your answers will always turn out the same. Any questions about anything? Node voltage analysis as a homework assigned to it. I believe it's due, I want to say it's due tomorrow, I think, because July 4th holiday is coming up. It's between our classes and I don't have any plans. I'll be working right through. But I still decided to give students a break. If you need any help with that homework, reach out to me, let me know. one other thing I wanted to discuss was the concept of supernode. And supernode sounds like some sort of, well, fantastical technique, but it's not. It's simply a shortcut. Okay. So if you ever see supernode, if you see more than one voltage source in a circuit, what you would do is, let's say you have, let's use the bottom node as a reference, right? You have more than one voltage source in a circuit. The obvious hiccup is that we cannot describe the current flowing through the voltage source using Ohm's law. If it's a resistor, we can use Ohm's law and say it's voltage for the resistor, VR divided by R. But if we have a current through a voltage source, we cannot describe that current using Ohm's law. So we cannot write a KCL expression. Make sense? Right? So all you're going to do is, let's say, let's call this IA and let's call this IB. You choose one end of that voltage source as your reference. In this case, the illustration has this bottom node as the reference. And the nodes are 1, 2, 3. So this is, let's call this 4. So this is reference. So V4 is equal to 0 volts. Okay. Now we have currents IA and IB going through it. If V4 is 0 volts because it's reference, then V3 is automatically minus 15 in this case, right? We cannot have more than one reference node for the same analysis. So what do we do about IA? Well, what you're going to do is you write KCL at both ends of the other voltage source. Okay, so let's call this IR2. Let's call this IR4. And this would be IR3. And let's use this direction, IR1. Okay, so you apply KCL at both ends of the voltage source. In this case, it's a 10-volt source because that's the one that is not connected to the reference node. And I can write at node 1, I have IR2 entering, IR1 entering, I have IA leaving. At node 2, I have IA entering the node, and I have IR3 and IR4 leaving. Applying KCL at both ends of the node, both ends of the voltage source. I have IR2 plus IR1 equals IA. And then at node 2, I have IA entering and IR3 and IR4 leaving. And here's the thing. If X equals A, and Y equals A, then I can state X equals Y. And so I can state from both of these equations, IR1 plus IR2 is equal to IR3 plus IR4. And thus we eliminated IA. And that's it. That's the concept. You apply KCL at both ends of the voltage source and you eliminate IA because we cannot describe IA using Ohm's law. And that's it. That's the supernode. All right, let's take a 10-second pause. Let me know if you have any questions. Any questions at all? Okay. All right, we have about 7 minutes left. Let's see, on to mesh current analysis. You know what? Let's just end class here for today. And then we'll pick up here again on Wednesday. Okay. Node voltage analysis is one of the, in my experience, students find this technique, to be particularly difficult. That's because there are a lot of concepts coming in. But again, remember at the beginning of this course, I stated, you learn new analysis techniques, but all of these techniques are based only on 3 laws: Ohm's law, KVL, and KCL. Node voltage analysis requires Ohm's law and KCL. That's it. The entire purpose of circuit analysis is simply to write out mathematical equations so that we can solve for the voltages and currents. That is it. In this case, we generate our equations by applying KCL. Hence, my emphasis on students doing the KCL homework at the beginning, KCL and KVL homework at the beginning. Okay, students need to identify the nodes, apply KCL. Make assumptions of the branch currents, apply KCL, generate your equations, and then express everything using Ohm's law and node voltages. Okay, so take your time, refresh your memory about, and not refresh your memory, review these slides after class, retain the steps. Let me know if you have any questions. The reason I'm taking it slow is, again, this is one of the most difficult and challenging aspects of circuit analysis techniques. Okay, and again, this is a guaranteed question on the final exam. Again, if students have not looked at the final exam page, I suggest or I recommend that you do so. This is a guaranteed 10-point problem in the final exam. Okay, setting up of node voltage analysis, drawing out the figure, marking the branch currents, node voltages, and then performing your solution and analysis is there on the final exam. Also a big homework and also a quiz on node voltage analysis. Okay. So we'll end class here today, and I will see you all on Wednesday. If you are taking the lab, we'll meet back here at 12:10, which is in about 15 minutes. Any questions?